Right, so today we're going to be looking at complex numbers, which is the first topic in further maths. So it's the first topic that you'll come across in A-level further maths in pure maths. So if you remember from normal maths...
So today we're going to be looking at complex numbers, which is the first topic in further maths. So it's the first topic that you'll...
All right, apologies for that. So it's the first topic in further maths, and what we're going to be looking at is having a look at, so if you remember when you did GCSE, when you've done A-level, when you've looked at quadratics, you've had your quadratic formula. So you've had x equals minus b plus or minus the square root b squared minus 4ac over 2a. And this formula sort of breaks. It just doesn't work when you had a negative discriminant. So by discriminant, for those of you that might not have come across it yet, I'm talking about this bit here. So if b squared minus 4ac ended up as negative, it kind of just didn't work. We'd say, okay, you can't take the square root of a negative number. It's impossible. Forget it. And before in maths, we said there's no solution. So now we're going to introduce to you a new number system. And that number system is the square root of minus 1, which equals I, okay? And what we do, we can then represent roots of quadratics in what we call real numbers and imaginary numbers. So an imaginary number is anything of the form something I. We usually use the letter B. So for example, you could have, if I gave you the square root of minus 3, that's the same thing as the square root of 3 times the square root of minus 1. So that would be root 3i, because the square root of minus 1 is I. So if we had the square root of minus 9, that's the same as 3i. And I is the square root of minus 1. So that's an imaginary number, and it's a different type of number. So that's what we call a complex number, is a mix of an imaginary number and what we call a real number. So that's what we're used to. So we say it's of the form. So complex numbers are of the form a plus bi, where the a bit is the real bit and the I is the imaginary part. So we say this is the real part, and this bit is your imaginary part. So an example would be something like 3 plus 2i. Okay, now there's lots of like practical applications for this. You're not going to worry too much about it, but if you end up going into physics and engineering, you use it in quantum mechanics and fluid dynamics and look like relative control theory. It's also involved in like pretty maths, because maths is really an art, you know, pretty maths when you're looking at fractals and really pretty things, and also you look at it in number theory. But let's first go to the basics. So the basics are, we're going to write things in terms of I. Now, if you think about it, you treat I like an X and a Y in an algebraic equation. All the I's stay together and all the numbers stay together, unless you end up with I times I, which will give you minus 1, because we're saying the square root of minus 1 is I. But let's go through some examples. So if I told you to write the following in terms of I, so we're going to have the square root of minus 9, the square root of minus 36, let's say the square root of minus 4. Now the square root of 9, like we just did, is the same as the square root of 9 minus the square root of minus 1. Sorry, I mean the square root of minus 9 is the square root of 9 times root of minus 1. So that would give you 3i. And in the same way, this is the same as saying root 36, root minus 1, so 6i. And this would be 2i. So that's giving you an idea of how it's very basic, writing things in terms of I. And the bit that you have to remember is that the square root of -1 is represented with this I here. Okay, so now let's take, say we had 2 plus 3i plus 4 plus 6i. So what we can do is we add the real bits together and the i's together. So 2 plus 4 to give us 6 and plus 9i. Okay, in the same way you treat it if you had a number outside the bracket, you would treat it in the same way. So say we had I plus 2 lots of 2 plus 3i. That's the same as I plus 4 plus 6i. So we've got 7i plus 4. So in terms of that, almost imagine it like an x. So now let's solve some quadratics where we can use this I. So let's have a look. We've got z squared, say plus 25 equals 0. So I'd say, okay, so that means z squared equals minus 25. Now, normally we'd say, oh, you can't do anything. But now we know that z is the same as the square root of minus 25. When we take a square root, we can get plus or minus. So we've got plus or minus the square root of 25, the square root of -1. So it's plus and minus 5i, because the square root of 25 gives us 5, and the square root of -1 is I. So in the same way, if you've got z squared plus 3z plus 5 equals 0, now you can plug this into your calculator. And do you remember, if you've ever plugged in your quadratics or used your calculator to solve quadratics for you and you end up with an I, the reason is this. So now let's think, if we put it into the quadratic formula, my A is 1, my B is 3, and my C is 5. So therefore Z would be minus B plus and minus the square root B squared minus 4 times 1 times 5 all over 2a, so 2 times 1. So it's going to give you minus 3 plus or minus, and then we're going to get 3 squared, which is 9, and then you're going to have 9 minus 20, which gives you minus 11 over 2. Now the way you'd write that is that's the same as minus 3 over 2 plus or minus the square root of 11 I, because root minus 11 is root 11i, all over, and that bit's over 2 as well. So those would be how you solve those quadratic equations, and you've introduced I now. So now we're going to start looking at, so we said if I is the same as the square root of -1, logically, I squared must be -1. So we want to express things in terms of, okay, so if I've got 2 plus 3i, and say I have 4 minus 2i, and I want to open out those brackets. So in exactly the same way as you'd open brackets out, you do 2 times 4 to give you 6, 2 times minus 2, so minus 4i. So I've got this times that, that times that. 3 times 4 to give you 12i. You've got a plus and a minus. It's going to make a minus. 3 times 2 to give you 6. And then you've got I squared. Now we said I squared, so this bit here is the same as -1. -6 times -1 is going to make this +6. And if I put together, I've got 6, I've got -4, so I've got -4 plus 12 to give me +8i, and then altogether I'll have 12 plus 8i, because I've got the 6 and the 6. But it's realizing I squared is actually -1. Okay. So now what I want you to think about, because this comes up, is, what does that mean? So if I know that I is the square root of -1, I squared, we said, is -1. I cubed is the same as I times I times I. These two bits together is -1. This bit is I, so it's the same as -I. Now, if I had I to the 4, that's the same as I times I times I times I. These two together give me -1. These two together give me -1, and I'm going to get +1. And then everything after that, we can think of multiples of one of these. So for example, if I wanted to do I of 101, I could say, well, that's the same as I to the 4 to the power of 25, so I've got to 100, times by an extra I. And because I know I to the 4 is 1, I've got 1 to the 24 times I, 25, sorry, and that's just going to leave me with I. So I break it down into smaller multiples. Okay, so that's an overall idea of what a complex number is. So it's a complex number, has your real, your imaginary, and there are ways to multiply things, and it's the concept of I. So now let's look at what we call a complex conjugate. Now, what a complex conjugate is if we have, so you've noticed I've started to use Z and not Y equals or X. Generally, with complex numbers, we use Z. So you'll notice we start to use Z, and I've got a Z, for example, is 3 plus 2I. And now I'm going to do the complex conjugate. And what that means is I'm going to change the imaginary bit. I'm going to change the sign of it. So it becomes 3 minus 2I. Now what I want you to do is think, what happens if I add those two? And what's going to happen if I multiply those two? So let's have a look. If I do Z plus Z star, I'm going to have 3 plus 2I plus 3 minus 2I, which is going to be 3 plus 3 to give me 6, and 2I minus 2I, which disappears, so I get left with 6. Let's try multiplying them. 3 plus 2I, 3 minus 2I. So you might notice it's a difference of 2 squares, but if you don't, let's go through it step by step. 3 times 3 to give you 9. 3 times minus 2I, so we get minus 6I. Then we've got plus 6I, and then we've got plus and a minus to make a minus, and then we've got 2I squared. Right, so these cancel each other, which is what you'd expect because it's a difference of 2 squares, so you'd expect the square of the first minus the square of the last. So we've got 9, 2I squared. I squared, I know, is minus 1. Minus 1 times minus 2 squared, so that's 4. So we'll get plus 4 there. So we're going to get 13. Now, what do you notice? Both of these numbers are rational, right? And I mean, are real. So you will have noticed when you do things in surds, so that's why I was getting to rational, and you multiply your difference of 2 squares with surds, you always end up with a rational number. So this is a way, this multiplying by the conjugate, where we can make things real. And we tend to do it on a denominator, like we do at surds when we rationalize the denominator. We're making the denominator, in this case, real. And that's what we do when we divide complex numbers. Let me show you. So if I had 5 plus 4I divided by 3 minus 2I. Okay, so what we can see is that we want a division here. Now, what this means is essentially get rid of the imaginary number on the denominator. So you're going to multiply top and bottom by 3 plus 2i. So it's kind of like I said, when you do surds and you rationalize the denominator. So we can multiply out the top and do the bottom. So we get 5 times 3. So we've got 15. 5 times 2i, so 10i. 4 times 3, 12i. 4 times 2, which is 8. And then we've got I squared, which is the same as -1. So all of that is going to become -8. But we'll do that in the next step. And then here we've got the square of the first number. So 3 squared, which is 9, minus 2i squared. Okay, so we know this becomes -8 because I squared is -1. So we've got 15 minus 8. So we've got 7 plus 22i on the top. And on the bottom, we've got 2 squared, which is 4, times by I squared, which is -1. So all of this is -4. 9 minus -4 gives you that it's minus to make a plus, so 9 plus 4 to 13. And you could write that as 7 over 13 plus 22 over 13i. Yeah. So the useful bit to remember, if you want to, is a plus bi, a minus bi is the same as a squared, and instead of minus b squared, because of this I, it becomes plus b squared if you wanted it generically. So we'll do, this is probably, you know, a lesson that would take you a few weeks at school. So this is just an introductory bit. The next bit, and we'll do that at another point, is taking this a little bit further when you then look at roots of quadratics, how they can be written, and then you have a look at cubics and quartics, which is like to the powers of 4. But this is the basics. It's a whole new way of thinking. And, you know, it's, you know, they were originally introduced by an Italian mathematician to represent the roots of polynomials which weren't real, so we can do different things. And so we'll look at some other roots later, and then also look at Argand diagrams, which are kind of like your XY diagrams, but they're how we plot those complex numbers. So I hope that was useful. If you're thinking of studying further maths, apologies for it not being perfectly, you know, prettified, but I will replace these slowly and do the entire thing in one video. Okay, well, good luck, and I shall see some of you tomorrow.